Any questions? Good. That's good. Okay. Okay, the last example we want to study is an online set cover. I will delete this one first. So here we have M sets, n elements. Yeah, so here the thing is that we don't know. Okay, remember this file. We are given these sets. In the offline setting, we are given like M sets and n elements, right? And we are supposed to cover all the elements by choosing minimum number of sets. Now we have some uncertainty because these elements will arrive online. So okay, maybe E1, E3, E4, like E2, like E6. Some elements may not arrive. Okay, so we don't know. Some elements will arrive or not, I don't know. But if they arrive, they'll arrive out of the universe of the elements. Okay, so of course, because you don't know which elements will arrive, so you don't want to buy sets in the beginning, right? Because you buy sets, like you build it in the facilities, but no one comes in, then that will be lost for you, right? And then here the requirement is that, like, say E of t is the element that arrives here. Actually, the fifth element. The fifth. Right? Then, so I'm assuming that at time 1, E1 arrives, at time 2, E2 arrives, and so forth, right? Then, at time t, right? All the elements, E1 through ET must be covered. Right? So when a new elements, if the element is already covered, no worries, you're happy. But when the element arrives, if it's not covered, you have to choose another set. Okay? So therefore you have to build another facility, right? So then, yeah, and then here the point is that once the set is chosen, it can't be unchosen. It's elliptical, right? Once choose, then it's done. Is that problem clear? Or so elements alive over time, but you don't know the whole. I mean, you know the which elements will arrive in. You know the universe of the elements, but some may arrive, some may not. Okay, but only one element is labeled at a time. Okay, so because we don't know which elements will arrive, you have to speculate, right? So and when E of t arrives, you have to cover it as soon as possible. Okay, and you want to choose the minimum number sets to cover all the elements that have arrived so far. So here I only give you in a sketch of the algorithm because the proof will be actually will differ to the homework, and it's a step by step homework procedure, so it won't be difficult. But anyway, just I'll go over the high level idea here, so you can get it. So we are going to use primary dual algorithm. So for simplicity, we are assuming that this J by yeah, I think so. Okay, so I think I should define this. Okay, let's say the U prime is a subset of elements that actually are alive. Okay, the U prime could be same as U, but we don't know. Okay, and this Xi, as usual, Xi means that, I mean, it's a if you think about IP integer programming, I mean the interpretation is right. If you choose the set I, set Si is chosen. Right, this is 1, otherwise 0, right? Okay, and Sj, Sj is I just define notation here. These are the sets. Set indices. So let me just define this way. So Si these are the set indices, right? That include the element J. Okay. So these are the sets that include J, but I just use indices because we are going to index this at S1, S2, and so forth. Okay. Then, if element J actually alive, then we have to cover it, right? By choosing one of the sets that include J, right? Good. And then as before, we can relax the integer programming by allowing this Xi to have fractional values. Then it'll become linear programming, right? So this kind of a fractional value, this is IP integer programming interpretation, but we are going to relax it. We did this in approximation algorithms, right? Good. Okay, then. Okay, now see, we don't know this LP, linear programming, in the beginning. Because, I mean, we know Xi, but we don't know if we'll have this constraint or not, right? Because we'll have this constraint only when the element J alives. If the element J doesn't alive, I don't have to cover it, right? So, these constraints will be revealed one by one. when a new element arrives, it will generate a new constraint. I have to cover the element. Make sense? Okay or no? Okay or no? Any question here? Does this make sense? No? It's good? Okay. So then, okay, so we can think about the dual of the linear programming. So it will be maximum I'm not going to cover it again on how we can derive the dual of this primal because we did this several times. So anyway, this is primal and this is dual. Okay. So here's the algorithm. So like if you think about deterministic algorithm, like initially all xi will have a zero value because in the beginning you haven't chosen any set. Okay, but when you over time you are going to choose a set. If you choose a set xi will have a value. Xi's value will jump from 0 to 1, right? But we are not going to do that. We are going to actually we'll first solve fractional second problem. So we are going to find it. So fractional second means feasible solution to the we're going to consider solution that is feasible to this linear programming. That's a fractional set cover because you can choose sets fractionally. Okay? So for example, let me give an example here. So this may look a bit confusing, but it's kind of triangle-like case. So this you have 3 elements here. Let's call this 1, 2, 3, and this say S3. This is S1 and S2, right? I mean, you know, to cover all these elements, you'll have to choose two sets, right? Maybe you can choose like S1 and S2, or S3 or S2. I mean, anyway, if you choose any 2 sets, then you can cover all the 3 elements, right? So the feasible integer problem solution, right, will be say like x1 or right. If you choose any of 2 sets, then you'll be okay, right? But now think about feasible LP linear programming solution, right? Then I can choose each set by half, right? So namely x1, x2, x3. If I set all these 3 variables to half, right? Then you can easily see that, hey, this set, this element 1, is covered by the set S3 by half, and this also is covered by S2 by half, right? I'm choosing every set by half. So in the fractional solution, it is allowed to choose sets fractionally. Okay? So I mean, here see this x1. To cover this y, I need to cover, as long as okay, this is x3, right? This is x2, x1. As long as this element 1 can be covered by this set S3 or S2, right? Therefore, as long as S2 plus S3 is at least 1, then it will be covered, right? So I'm allowed to have a fractional solution. That's what I mean by fractional set cover. Okay, so we can convert to fractional LP set cover solution to the like this kind of integer solution, like over time online, but we're not going there, okay? Because it's a I think that's a bit like some off topic, okay? So anyway, is the problem clear? So the elements alive, I won't solve this linear programming, the fractionally. Okay, this also makes sense, right? Because like so far our example was, hey, is we building this facility like or not? But that's integral setting, right? Discrete setting. However, you can buy something right here, right? And then you can fractionally buy, and as long as you can provide some like supply, like supplies to this, like client say one, by buying this as x2, then that's okay. So it's like a kind of fractional argument. So basically, we're kind of considering this a divisible setting. Okay, good. And then the question is that how can you solve this? Linear programming online? We don't see the whole constraints a priori, but somehow we want to solve the linear programming online. Does it make sense? Okay, so I'll just describe the algorithm, and then it can give you a sketch of the proof, but the details you should be figured out by yourself because it'll be a homework problem. Okay, so what do we here? Yeah, so I think we also should set this yj is yj. Oh no, this is. I think we should set this one. I'm sorry. Yeah, I'm sorry. Yeah, yj is 0 or j, and then this becomes this. Yeah, this becomes 1. So, okay, initially, we didn't choose any sets, right? Therefore, we're going to set xi to 0, okay? And also yz will be 0 in the beginning. Now, when a new element j arrives, okay, we are going to have a new constraint because we have to cover the element, right? So what do we do? Well, we first see that if it is already covered or not, right? So namely, I need to look at the constraint. If this constraint is already satisfied, namely, if the j is already fractionally covered by set I've chosen, then do nothing, right? So otherwise, it's not fully covered. And fully covered means that it should be at least 1, right? It's not fully covered. I have something. So what do? I need to increase it. I need to get by. I need to choose more sets, right? I need to bump up the xi, right? that includes element j. Okay, well, how much? So I increase this by xi plus 1 over x, 1 over s of j. Okay, so what does this mean, right? This j, this j is there can be like multiple sets, right? That include j. Then, and then, 1 over s of j, right? This is 1 over the number of sets that include element j. Okay, so I increase it. The xi is increased by this, right? Plus xi. So like what does this mean, right? So if you don't have this, right, it means that you're doubling xi. Right? The change of xi will be xi. So you're doubling. But you are also doing one more here. You are just adding this term, which is 1 over the number of sets included element j. So like, think about this, right? Okay, so here in this example, there are 3 sets, right, include j, right? If I choose every set here by 1/3, right, then I can surely cover this, right? 1/3 by each set. That's what I'm doing here. And on top of that, I'm also doubling xi in some sense. Okay, and then this has nothing to do with the algorithm itself, but for the analysis, we just reset yj to 1. Okay. Is that reason clear? Okay, good. Okay, and then the homework problem will give you ask specific questions, the steps to you you need to show. The first it asks you that, hey, show that this xi is a feasible solution, right? But it's kind of trivial because this, right? Because if element j is not covered, I bumped up the sets that include j by 1 over the sets I 1 over the sets that include j. They will be covered, right? So yx is feasible. You can show it easily. And then 2, you can also show that primal and dual objectives are not very different. They are different by at most factor 2. So how do we do that? I'll give you some very high-level sketch. Again, you can. It's a homework problem. So remember that in skill rental problem, we show that primal dual increase by at every time step, and we show that the primal objective increase can be bounded by the dual in objective increase. We can do the same thing here. And third condition is some algebraic, so I'm going to skip that. And then the last one is that unfortunately y will not be feasible. Okay, so y, if you add up this yj, it will be too big, so you have to scale down. Okay, to make it feasible. Then because you scale down, so this initially we have some this x solution. This is primal, and this is dual, right? But this is not feasible dual solution. So you have to scale down a lot, this dual, like a y prime. Y prime is something like y prime is something like y divided by say like log hours, log like something like log n. Then you can show that this is feasible. And then now then this gap between dual and primal is 2. Now because you scale down dual a lot, so there'll be more gap between dual and primal. Okay, but you can show that the primal is like overlog log m times the dual, and then that'll be the end of the homework question. Okay, that's the sketch. Okay, so I want to kind of wrap up this online algorithms now. So we covered several examples: skill rental problem, online paging, and we briefly touched on online set cover. So okay, so here I think some like highlights is that sometimes you want to use some randomization to hedge against uncertainty in the future. Okay, and this is also by using primal dual, by updating primal dual, you can design algorithm. But anyway, this is also kind of a criticized sometimes because here we are thinking about we are trying to develop algorithm that is a kind of that works against like all possible, like worst case possible future inputs, right? But they can be too pessimistic, right? Therefore, people like trying to understand what, like if you can design better algorithms under reasonable assumptions. So in the case, people try to kind of relax the the input. For example, hey, what if like these elements y alive in random order? Like see, you think about the sequence of like your customers, right? I mean, they are not going to like collude, right? In most cases, to like present the worst possible input for me, for my business. It's like in most cases, it's kind of random order. Then what happens? Or like like for set cover, like maybe you can have some predictions, right, for the future. Okay, so I know that in the past, if similar settings are repeated, then I know that I have some rough idea that which elements will likely alive. Okay, using such information, can I do better, right? So this kind of also like designing online algorithm using like predictions, machine learning predictions. This is also a very hot topic. So if I have time later in the semester, I'm going to cover that quickly. Okay.